Hello, my young friends, or old friends. Welcome back to the show. My name is Dustin Allen Fife, and I am your beautiful, wonderful host today. Today we are talking about mixed models, version 3. Aren't you excited? But what's more exciting, perhaps, is the fact that we have a very special guest today. Please welcome Jack Attack Mac from the radio show 108.2. The Jack. Ladies and gentlemen, thank you for having me on your show. It is quite a pleasure. So let me ask you, Mr. Jack Attack, why is it that you're here to talk about statistics? Well, why not is what I want to know. Okay. So we have a radio talk show host here to talk about statistics. Let's turn to the PowerPoints, shall we? Yes, ladies and gentlemen, we have today a brand new, all new, totally awesome version of mixed models, the version number 3. So today's learning objectives for you are 3+ different sources of variance. So be able to identify all 3 sources of variance. And then we need to understand model comparisons in mixed models. Level 1 variance explain, what is that and why is it important? Level 2 variance explain, what is it and why is it important? And then how do we compute p-values with a likelihood ratio test? What is the BIC? And how do we use it for model comparisons? And finally, what is the Bayes factor? And how do we use that for model comparisons? And then finally, we're going to talk about a model building strategy, where we compare the variance explained. Excellent work, thank you. I really appreciate that stunning introduction. Wow, I've never been more excited about mixed models in all my life. Okay, so 3 sources of variance. We have variance in predicting individual scores. Okay, you remember we have dots that deviate from the predicted lines, and the deviation of those dots is representative of the variance in predicting individual scores. We also have variance in predicting cluster intercepts, because remember the intercepts may deviate from one cluster to the next. And so the variability about the mean or the fixed effect slope is what we are talking about there. And then we also have variance in predicting the cluster slopes. Those slopes are going to change from one cluster to the next, and what is the variance of that slope? Likewise, how do we know if a predictor is worth keeping? We can measure the reduction in unexplained variance just like we do with an R-squared. So by adding a predictor, it's going to reduce our variability in predicting the individual scores or predicting the slopes or predicting the intercepts. And so we're going to be able to identify the change in R-squared when we add a predictor. But these probably should be mapped into the appropriate sources of variance. So when we do model comparisons in HLM, we're going to be using 3, well, I forgot to put one up there. We're going to be using 4 metrics. We're going to be using change in R-squared as we add this predictor. We're going to be using p-values. Did I just say we're going to be using p-values? Ah! Yes, we are. But we'll explain why that's a little bit more okay in this situation than it would be in other situations. And then we're going to talk about the AIC and the BIC, and again, we're going to talk about the Bayes factor. Okay, so when we are talking about intercept and slope variance, let's say this is our model in R. We got math achievement as a function of sex, minority, and socioeconomic status. Now remember, these are the fixed effects on the left, and then on the right in the parentheses, those are the random effects. And so it turns out that the fixed effects will reduce intercept and slope variance. And by the way, it'll probably also reduce individual variance because these elements of the model, the fixed effects and the random effects, are going to be correlated. So here's another way to think about it. So if you look at the mathematical notation on the right, that is the math ease version of the model. So we got math subscript ij is equal to a random intercept plus a random slope plus, or times sex, which is a random effect, plus B2J times socioeconomic status, which is a random effect. And again, we see sex and socioeconomic status as random effects, or you could say those are individual level predictors. But then we also have these fixed effects. And another way to think about it is we are putting them in as level 2 predictors, or in this case, we're looking at schools. So these are predicting the school slopes and the school intercepts. Okay. So those are our level 2 predictors. We've got sex, socioeconomic status, and minority. Oh, I forgot the subscript J on minority, but you get the idea. So this is telling you, for example, so this is the intercept. So the intercept is a function of a fixed intercept plus a fixed slope for sex. So we are using the composition of sex in school J to predict the intercept, but that has its own slope. So it's kind of weird that we got a slope predicting the intercept, and then we got a slope here predicting the intercept from socioeconomic status, and then we've got a slope here predicting the intercept from minority status. And so each of these three things, what are they going to do? Well, look, we are predicting the intercept. So these three predictors here are going to reduce our unexplained variability in the intercept. That is right. That is exactly right. We are going to reduce that variability. And likewise, we are going to reduce the variability in our slope for sex. And in this, we're going to reduce our slope for socioeconomic status. Yes, thank you. It's so much more exciting when you say it. Okay, and so here's another way to think about it. So in here is the R output. In this section, we have the random effects, and we have our random effects intercept right there. So that is the variability about the intercept. And so when you include these three predictors, not surprisingly, that variance is expected to go down. And likewise, when you add sex, so this is just telling you what the referent group is. So it's saying it's males are the referent group. And so when you include male as a predictor of, when you include sex as a predictor, okay, let me back up. When you include these blah, 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 blah. Sorry, what I'm saying here is that the intercept has variability, and that is representative of its variability. And these predictors are going to reduce the variability of the intercept, the variability of the slope, and the variability of the other slope. Makes sense? Hopefully that wasn't too confusing. Okay, so taken together, these three predictors, sex, minority, and socioeconomic status, will reduce our variance in estimating the slopes variance and the intercepts variance. So here is how you would show it in R. Again, these are the fixed effects, and these are predicting the variance in the intercept and the two slopes. And then here are the numbers in the output in R. So hopefully taken together, that makes sense. Now let's talk about the individual level variance. So before we were talking about the fixed effects, which are the school level effects, and those are going to reduce our estimates of the variability of the intercept and the slopes. Now we're going to talk about the individual level variance. So we would expect that these predictors, sex and socioeconomic status, now let me take big step back, big picture here. Remember, the fixed effects are, I totally lost my train of thought. It kind of came back. So the fixed effects, so anytime we put a fixed effect here, we are saying this is common among all schools. And anytime we put something in here, we are saying that within a school, they're going to have different slopes for sex and different slopes for socioeconomic status, and implicitly, there's a 1 there, or R defaults to saying that there is going to be variance in the intercept. So again, each school is going to have its own sex and socioeconomic status slope and its own intercept. So I guess the one thing that isn't is minority status. So we are assuming minority is a fixed effect here, that the difference between minorities and non-minorities is constant across all schools. There's no variability from that. Okay, so now that we have taken the big picture approach, let's go back here. So again, sex and socioeconomic status, we expect that those vary, those slopes vary across schools. Every school has its own difference between males and females and its own predictability of math achievement from socioeconomic status. So you might, for example, say that some schools are better at supporting their females in math achievement, or supporting those who are lower in socioeconomic status than other schools, that sort of thing. So again, back to individual level variance. Now remember, individual level variance means the deviation of the dots from their respective school prediction. And so when we include these individual level predictors of sex and socioeconomic status, those are going to increase our precision in predicting the individual data points. And then mathematically notated right there. So we are saying that these variables, sex and socioeconomic status, this is just like the regression that you are used to. When you include a predictor, it's going to make that line closer to the individual data points, which is going to reduce the amount of unexplained variance. Y'all with me? Any questions? Oh, by the way, I've been working on this new technology that I can hear your questions. I can intuit your questions. I am ESP like that. So any questions? Okay, I heard that. That'll be explained in the next slide. There you go. Got it? Okay, good. So this variance right here, 35.6499, that is the residual variance, or the deviation, the average-ish deviation squared of the dots from the lines, and that is its value. So yes. So again, adding those predictors will generally decrease that residual variance. And again, taken together, so here's the notation in R. So these two predictors are the individual level predictors. That's how they show up in the math version. And then they are going to generally reduce that. A-okay? Variable selection strategies. So we are going to talk about using model comparisons to identify which variables to include in a model. So here's the basic idea, ladies and gentlemen. We want to know whether keeping a predictor, for example, a predictor of slopes or intercepts or of individual scores, is worth keeping. And so what we want to do is we want to add a predictor, and we are going to either add that at level 1, which is the individual level, or we are going to add that at level 2, which is the cluster level. So we then compute the proportional reduction in variance relative to a baseline model. For example, we usually use as the baseline model a random effects Anova. You remember that is the model without any sort of predictors. So remember also that statistics really sucks at answering which model is right. However, it is really good at comparing which of two models is better, especially if the models are nested. We can determine whether spending 1 degree of freedom improves fit enough to justify the cost of that 1 degree of freedom. So, ladies and gentlemen, without further ado, let me go ahead and show you in R how to do model comparisons. Man, that is good stuff right there! Woo! Ought to have you on the show every time. So, model comparisons on R. Here's how we're going to do it. So, in the left, we see that we have a random effects Anova model. So first we're going to require lemur 4, or LME4, I guess, and then we're going to use the lemur function. So just as I showed you, I think it was last week, we have math achievement tilde1, which says just fit an intercept, or in this case, just estimate a mean. and then allow the mean to differ between schools. So that's going to be our baseline model. And then now we're going to do a second model called mod.ses, where we are just going to add the predictor socioeconomic status, both as a fixed effect and as a random effect. And then we've got this super wicked awesome function called improve.fit, thanks to yours truly. Yes, ladies and gentlemen, yours truly. I mean, not yours truly, but Mr. Fife here has created a function in R to make this absolutely easy. Thank you, sir. Exactly. So the improve.fit function, it takes just two arguments, mod.ses and baseline. And what it does, if you look on the right here, is that tells you the change in R squared by adding whatever you added to the first model here. So in this case, this is SES at the fixed effect level and at the school effect level. And so what we see is that by adding socioeconomic status, we explain about 6% of the variance of the individual data points from their respective line. And we also reduce the unexplained variance in the intercepts of the model. So each school, we're able to predict its mean a little bit better by an amount of 44% of the variance. Makes sense? So that's the basic idea. It's actually super simple to do in R, at least with the improve.fit function. Not to toot my own horn or anything, but that's exactly what I'm going to do because it's awesome. So we explained 6% additional variability in level 1 variance, and we explained about 44% additional variability in mean differences, or the intercepts. So yes, these are interpreted just like an R squared measure. But now we have to specify which variance we are referring to. Are you reducing the variability in person variance? Are you reducing the variability in slope variance? Or are you reducing the variability in intercept variance? And by the way, there could be multiple slopes in the model. So you might estimate the reduction in variance for the slope of socioeconomic status or minority status or gender or whatever. So the definition of R squared gets a little more complicated when you're talking about mixed models. So let's go ahead and look at another model just as an example. Let's see if I have little, yay, I do have arrows. Okay, so let's go ahead and add to the existing model sex both as a fixed and as a random effect. Again, here is our fixed effect here, meaning every school has a sex effect. And then over here, we are saying, but schools are allowed to deviate that. So some schools have a greater difference between sexes than others. And then now we're going to compare it to the baseline model. So now this model comparison here is going to say, all right, what happens when we add socioeconomic status and sex, both as fixed and random effects? And how does our fit improve relative to a model with absolutely no predictors? And then here in this second one, we are looking at, all right, before we had SES, now what happens when we include gender in addition to SES? So that's comparing it to a different baseline model. And so in the first one, we had 6.8% of the variance is explained with socioeconomic status and sex relative to a baseline model with no predictors. And then our variability in the intercept is improved by about 53%. Now, when we compare the socioeconomic status model to the socioeconomic status plus gender model, we explain a fraction of a percentage of the variance in the residual, and our intercept variance improves by 16%, and then our socioeconomic status variability improves by 19%. But here's an important caveat here, is that these values are now relative to the SES only model. So relative to the model with just socioeconomic status, we had some amount of variance unexplained. Now we have cut that down by 19%, again, relative to the baseline model, which in this case was socioeconomic status. And so what will tend to happen is as you include more predictors and then compare it to a model with slightly less predictors, you're probably going to explain less and less of the variance, if that makes sense. But if you were to compare it to the baseline model, then whoopee, that's going to be big. Okay, so other metrics. So far I have talked about a R-squared like measure, but we could also look at other metrics. We can also compute a p-value, but this is a model comparison p-value. So in this case, a p-value ain't a bad word in my class. Okay, that was awkward. And then, anyway, so this is a model comparison p-value. In other words, so let's assume the full model is just noise. What is the probability of obtaining a fit like this if it were just noise? And so this is a different question than the standard null hypothesis significance testing, where you say that nothing at all is going on. Now let's add a single predictor and see if that deviates from 0. So I'm much less opposed to these sorts of p-values than standard NHST computations, because with NHST you're setting up a straw man. What? Leave me alone, IT! Sorry. I'm in the middle of a video here. Where was I? Okay, so again, p-value, you're setting up a straw man. You're saying, all right, these correlations, you're testing, like if you're testing a standard correlation, you're testing against a correlation of 0. Well, nothing is correlated at 0. That's just a weird thing to set up as a baseline null model. Whereas in here, we're talking about model comparisons. If you read that Joe Rogers model comparison revolution paper, this is exactly the sort of thing that we're doing. We're doing a model comparison where the null model isn't no longer a very basic, really dumb model. Now we are saying a null model is actually a model with some predictors, and we're trying to see, all right, does adding this extra predictor, is it worth it? So we can use p-values in this situation, and I'm much less inclined to be cynical about them and criticize them. However, these still suffer from a lot of the same problems that all p-values do, is you're still playing a game of chance here. And multiple comparisons, you're going to get something, if you do multiple model comparisons, you're rolling the dice multiple times, so just by chance some of these are going to be significant. But again, it's psychologically a better problem to think about than a null of nothing going on. Okay. But we could also compute AIC and BIC, and it turns out that when we compute a p-value and do a model comparison, it also gives us the AIC and the BIC. So in R, let's go ahead and see how to do this. We've actually seen these before. I've said before that Anova is the model comparisons function, and so we've got the mod.ses and then the baseline. So you are doing a model comparison and saying, all right, is it worth keeping socioeconomic status relative to a model that has no predictors? So that's kind of sort of in a way a standard NHST model. And then let's see if I have any arrows. Nope, I don't. Okay, so I'll go ahead and explain this. So this is just a Anova summary table. So you would read it similar to how you would read any Anova summary table. This just tells you what formula or what is in each of the models and how the formulas look and that sort of thing. But really what we're interested in is this area right here. So that shows us that the baseline model spends 3 degrees of freedom. That is its AIC value. That is its BIC value. That is the log likelihood, and that is the deviance. Don't worry about those. Fortunately, because we're in R, we don't have to actually know what a log likelihood is. If we were using this in SPSS, SPSS doesn't do model comparisons, so we'd actually have to compute the model comparison by hand. But fortunately, y'all are R users, so what up? This is awesome. Okay, so that's the baseline model. It spends 3 degrees of freedom. With the socioeconomic status model, it spends 6 degrees of freedom with an AIC of 46,646. We don't really know what these mean, and they vary from model to model, but remember that smaller values is better. So both the AIC and the BIC favor the socioeconomic status model. So even though we're making the model more complex, it is worth it because it is improving our fit enough. And so that is your p-value, which is written in scientific notation, which is ridiculously small. So this p-value says, okay, if the null hypothesis is true, it would be very, very unlikely to obtain a fit as good or better as mod.ses, again, if the null hypothesis were actually true. So this tells us we should favor the socioeconomic status model. Now, let's compare the gender model with the socioeconomic status model. So now this is more in line with a model comparison. We are asking, all right, we know that adding gender is going to make it more complex. Is it worth it? Do we really need that additional information? And if we jump straight to the p-value, that says if we are doing the standard heuristic of null hypothesis significance testing, this tells you that yes, the models are significantly different, and therefore we choose the more complex model. But if we use a more informative AIC or BIC, you'll notice that in both cases, the AIC and the BIC are smaller. So again, that tells you that the gender model is better. So yeah, we add some complexity to it. Oh, by the way, that degrees of freedom right there. Oh, there's my mouse. So this says we spend 6 degrees of freedom in the reduced model, as we call it. And then in the full model, we spend an additional 4 degrees of freedom. And yes, it be worth it, folks. Unfortunately, in this situation, the AIC, the BIC, and the p-values all agree. And so it makes it a lot easier to make the decision when all these metrics agree. So let's talk about another metric for a minute. So perhaps there is a better way to compare models through what we call the Bayes factor. So the unfortunate thing with AIC and BIC is the rule of thumb is, all right, smaller is better. Okay, they're really, really close. Is that close enough? And you want to know, okay, is it like super better or is it just a little bit better? And it really doesn't tell you. Well, Bayes factor is a much more intuitive metric. And so what it tells you is it is a odds ratio. So it tells you the probability of the full model divided by the probability of the reduced model, or vice versa. So a Bayes factor of 2 means that the full model is twice as likely as the reduced model. And likewise, a Bayes factor of 0.2 might mean, it depends on which model's in the numerator and which one's in the denominator, but a Bayes factor of 0.2 means that the full model is 1/5 as likely as the reduced model. Or the reduced is 5 times more likely. So I actually understand, I think this is probably just human nature. I have a hard time thinking about 1/5 is likely. I'd much rather see a positive number. So sometimes I can flip those, and I'll show you how to do that in R in a minute. And so anyway, that's the basic idea behind the Bayes factor. And it turns out that we can approximate the Bayes factor using the BIC. And that is the formula right there. And, oh, scary! Math is scary! There's a formula! It's okay, people, because I've done this in R, so you don't have to worry about that formula. So in general, Bayes factor greater than 10, so the whatever model is in the numerator is 10 times more likely than the model in the denominator. The rule of thumb is that there is strong evidence in favor of the model in the numerator, or likewise a Bayes factor less than 0.1 says strong evidence in favor of the model in the denominator. So in R, how do we do this? Another fight for function, baby! We do bf.bic, which stands for Bayes factor.bic, and then what we do is we put the full model first, then the reduced model, and then, well, I guess I believe it can go either way. And then what we can do is there's that option that says invert equals true, which says, do you want a positive number or a negative number? And my camera likes to just turn off all of a sudden. Apparently my camera's getting bored by me talking, so that means I need to bring back in the radio announcer guy, I guess. Yes, ladies and gentlemen, so like Mr. Fife was saying, this tells you that in both cases, the full models are mega superior. So, in summary, for these models, we compared the baseline versus the socioeconomic status model, and then we had 4 metrics that we compared. We looked at the change in R squared, and then we saw that 6% reduction in the residuals and 44% reduction in the intercept, which leads us to conclude that socioeconomic status is probably important. Likewise, we used a p-value which told us that our p-value was very, very much less than the 0.0001 threshold that we might be interested in using, in which case that tells us again that the socioeconomic status model is to be favored. And likewise, we use the BIC, and if we compare the BIC values, this tells us that socioeconomic status is, once again, the favored model. And likewise, finally, we use the Bayes factor, which was 6 bajillion, or something like that. And that tells us that, again, the socioeconomic status model was the preferred model. Exactly, folks. So we also did a model where we compared SES alone versus SES plus gender, and those are the metrics for the change in R-squared. We got 0.9%, which wasn't that much, so we weren't improving the individual regression lines for the schools, but we were improving the residual variance, or the intercept variance, and the socioeconomic status variance. And so that told us, you know, with a 16% reduction in R-squared and a 19% reduction in R-squared, that tells us the more complex model is to be preferred. Likewise, the p-values told us that the more complex model was to be preferred. And then with the Bayes factor, it said super preferred the more complex model. So far, hey, they are congruent. Yay. Now, sometimes you might get a situation where the p-values disagree. And so if you look at the R code on the left, let's see. Okay, so I'm comparing, all right, I'll get there in a minute. So we've got a baseline model where we have no predictors, and then we have a model A where we have socioeconomic status, sex, and minority as fixed effects, and then socioeconomic status as a random effect. And then model B, we have the exact same fixed effects, but now we are adding minority as a random effect. And so we want to possibly compare A versus B. And so in the first code, we are comparing A versus B and saying, all right, does adding minority as a random effect improve the fit enough beyond the baseline model, which in this case has 3 fixed effects and 1 random effect? And what that tells you is you're explaining 0.6 of the variance in deviations from the lines. And then the intercept, you're explaining an additional 13% of the variance in intercept, and then 70% of the variance in slope. And then what you might do is you might compare the B model to the baseline, and then see how much it improves relative to the baseline, relative to the change in fit for A versus the baseline. So that makes sense? So we have 2 comparisons. The full model against no predictors, and then the reduced model against no predictors, and then looking at the change in R-squared, or the change in R-squared, if that makes sense. And so if we look at that, it seems that we improve fit relative to the baseline model. We are only improving by 0.5%, and we are only reducing the variance in the slopes by about 6%. And so you might say that 6% of the variance in the intercept might not be enough. And I didn't happen to set a decision criteria in advance, so you might say that, I don't know, 6% ain't worth it, so maybe we'll choose model A in this situation. And by the way, here we might say, let's choose model B because, I don't know, 17% sounds like a lot. And then if we were to do an Anova, or I'm sorry, not an Anova, a model comparison using the Anova function, and compared them, it might say, so we've got an AIC, so that tells us the more complex model is better, and the BIC says that, oh, it kind of flips. So look at that. So the AIC said model B was better, the BIC says model A is better, and then the p-value says model B is better. Because again, anytime there's a significant effect, that tells you to choose the more complex model. So the p-value is saying more complex model, the BIC is saying the less complex model, and the AIC is saying the more complex model. And then if we did a Bayes factor comparison, it tells us that, loosely translated, that, let's see, oh, that's saying choose A. Now, does that make sense? Actually, I don't think that makes sense because the Bayes factor, okay, so I made a comment wrong. So the Bayes factor is saying choose model B. It is 442 times more likely. Again, that's loosely interpreted. I don't trust a Bayes factor that big when there's so much disagreement. So I think, oh yeah, and that was just basically what I was saying is this because BIC is picking up something that the other ones aren't picking up, or is it really picking up something, vice versa. So is this because Bayes' factor is only an approximation, or is it really picking up something that the others are missing? So we've got disagreement here, and I'm not exactly sure what to do in this situation. You've got different metrics that have different assumptions that are disagreeing on what you ought to do. And so I guess my recommendation in this case, if you were publishing a paper, you would probably report the results of all the metrics, and you could make your own decision based on your own logic. Like you might say that, as I recall, BIC penalizes model complexity more than the AIC does. So the AIC tends to be, it's not as easily persuaded as, the AIC is more easily persuaded by an improvement in fit than the BIC is. So you might say, all right, I prefer cross-validation accuracy. And as you remember from our regression lesson, the more predictors you have, the more you're going to hurt your cross-validation accuracy. So you might say, all right, I'm going to go with a simpler model. In other situations, you might say, well, I'm more inclined to go with a more complex model because I want to make sure that I don't miss anything. So it depends on the assumptions, and it's a judgment call. And by the way, that's one of the problems with p-values is they take away the judgment, the opportunity to make judgment calls. It's a mechanical decision. Well, let's put judgment back in. It's your substantive area. You are the expert, so you ought to be the person making the judgment calls here. Okay, so comparing non-nested models. So far we've only compared nested models. What about non-nested models? So R will tell you, R will let you use the Anova function to compare non-nested model, but that doesn't make any sense at all. If you're computing a p-value comparison, you can do it. R will let you, but it doesn't make any sense. And to see some discussion on that, go ahead and go to stackexchange.com or the stats.stackexchange.com. And likewise, it doesn't make sense to talk about an R squared because you're comparing apples and oranges at this point. But you can use the BIC and the AIC, and you can use the Bayes factor. And not sure what that was about. So here's an example. So you might, for example, say, what is a stronger influence on drinking? A parent being a child of an alcoholic, or so your parents or your peers? What's going to be a stronger influence? So using the ALK use data set, we can compare two models where we've got peers versus parents, and we're just going to see which one is better. And so we could look at the BIC of the peer, BIC of the parent. And so the BIC, let's go ahead and look at this, make sure that my comments are right. So the BIC of the peer is a smaller value than the BIC of the parent. So that tells you that peers have a stronger influence than parents do. And if we were to do the Bayes factor, which we are permitted to do, it tells you that the peer model is 1,329 times more likely than the parent model, loosely interpreted. Yes, ladies and gentlemen, this concludes our PowerPoint and our lesson. So make sure you understand the following learning objectives, the three plus different sources of variance. For example, that could be the individual deviation from their respective school slopes. It could be the variability about the intercepts, or it could be the variability about the slopes. Likewise, we talked about model comparisons in mixed models. Level 1 variance explained, which is the individual level. And then we talked about the variance explained in level 2, which is the intercepts and the slopes. We also talked about p-values with likelihood ratio tests. And then we talked about the BIC. And we talked about our approximation to the Bayes factor. And finally, we concluded with our model building strategy, where we ask ourselves, is it worth it to include this additional predictor? Or we have two different models and we want to know whether one is better than the other. And we have various metrics we can use. We can use the p-value, we can use the BIC, we can use the AIC, and ladies and gentlemen, we can use the Bayes factor, not to mention the change in R squared. Enough talk, let's fight. So go ahead and on your own, if you want an opportunity to do that, go ahead and analyze using the math achievement data set. First compute the ICC, then determine whether schools differ in math achievement after controlling for SES of each student. And be sure to test whether a random socioeconomic status is necessary. Compute pseudo R squared, which is what we've been talking about, to see if SES has a large effect. Then let's add gender and do the same. And that will probably, I haven't actually created your homework yet, but I'm going to do that today. So that'll probably be your homework assignment. So ladies and gentlemen, thank you very much for joining us on this like super exciting day where we had such a fun fella here. Thank you very much. It has been my absolute pleasure to join you today. Now remember to stay tuned to The Jack 107.2. Or whatever we said earlier. Yeah, give this guy some shout outs and stuff, you know? So thank you for joining us, and we will see you next time.